look into different sources, with today focusing on the AC source. Not so much an AC circuit yet, but an AC source. So before we get into that, last time we talked about the 4 different types of dependent sources. So we can have both a voltage-dependent voltage source, a voltage-dependent current source, a current-dependent voltage source, and a current-dependent current source. And all of those follow some general format where we have whatever the type of source it is, times some type of gain, times whatever the dependence is related to. And these are just different types of sources that you can have. We will not see them moving forward in this class, but it's nice to acknowledge all the different things that we can have. So any questions about our different dependent sources? All right, so today we're going to talk again about the AC source. We are going to be focusing on sinusoidal AC sources. We will briefly talk about a couple of the other types of sources next week on Tuesday, but today we're going to focus on the nicest possible case with the sine wave version. So first, the symbol that we're going to be seeing for an AC source is we are going to be seeing a circle. So again, this is a independent source. We do put that inside of a circular shape, and we draw a little squiggle inside of it, which looks like a sine wave, because this is going to be an alternating source value, and it's going to oscillate back and forth between our values. So with going through and doing these, sinusoidal voltages are some sort of oscillating values between positive and -1. And with that, there's a lot of different ways that you can generate an AC source. So for example, you can have an electric oscillating circuit due to its motion in a magnetic field. You can have just a physically rotating AC generator, which is a just rotating electrical machine. Bunch of different ways you can go through and have alternating currents. As with our direct current sources, we're not going to really care exactly how they work. We're just going to care about how they go through and interact with our stuff. So if we look at this graph here, this is a standard sinusoidal function. And we can see in the y-axis, it's going to be either current or voltage. And along the x-axis, that is going to be our time. And often with the time, we'll see that in either milliseconds or in seconds, depending on the oscillating time period that we have. So for the positive maximum, right, we can go through and we can look at our sine function. When does sine reach a maximum, and what is that value for the maximum? It's the maximum value we can get out of sine. Yep. And when does that occur? I did sine what? What would I need to put in to get 1? In either degrees or radians, I don't care. It's not 45. That gets the square root of 2 over 2, or 2 over square root of 2, something, no. Because that's, yeah, it's gonna be at 90. If we're looking at degrees, at degrees, or pi over 2 if we're looking at radians. What is the negative maximum value we can get out of sine? It is -1. And what are those, what's that angle in degrees? It is 3 pi over 2 in radians. It is 270 degrees. Right, so 90 plus 180, getting us to that 270. So, right, these are gonna be our positive and negative maximums. You are going to see, especially as we get a little bit further, we are gonna start using radians with respect to talking about our AC sources. So we're gonna be seeing that pi over 2 and the 3 pi over 2. I don't wanna say every time, but it's gonna show up rather often. And with this particular function, it's being drawn as a sine wave. However, any sort of smooth wave that looks like this doesn't necessarily have to start at 0. That is referred to as a sinusoidal waveform. So even if we have something that looks like cosine, so we're starting at our +1, going to -1 and back, that is still referred to as a sinusoidal waveform. It doesn't have to exactly be sine for it to be sinusoidal. Anything oscillating back and forth in a nice, smooth way, we will classify as sinusoidal. So with this rotation here, with our value, if we're looking at this, again, this particular one, I would start at 0 current or voltage, go to whatever the maximum current or voltage value happens to be, down to 0, down to the negative maximum, again, current or voltage, whatever it happens to be. And so with this, we want to go through and make sure that we're understanding what is going on with our circuits. So before we get into that, any quick questions about sinusoidal waveforms? So when we talk about our waveforms, we do want to discuss the polarity. So if we think about what we were doing with resistors, sometimes we looked at the polarity, so where's the positive and where's the negative signs, to go through and then figure out, do I need to add or subtract that particular voltage? So now with having an AC source, that polarity is going to flip as the source flips as well. And so for the positive portion, so that's going to be where we have a positive, in this case, it's being drawn with respect to voltage. A positive voltage is going to cause the current, in this particular case, to be going around the loop in the clockwise direction. So it doesn't matter where I am kind of along this path here, as long as I'm somewhere, the current for this particular circuit would be going in the clockwise direction. So for half the time, we are going to be going clockwise. What do you think happens when we get into the negative side of the sine wave? What happens to the current? It flips directions. So if I'm flipping the polarity of my source, I'm going to be flipping the direction for that current. So with both of these here, right, the direction is going to be flipping back and forth anytime we're reaching a 0 value. However, the value for that particular current is always going to be changing. So as I'm going through, when I'm crossing with the zeros, there's going to be no current, but then it's constantly changing from 0 to whatever that maximum or negative maximum is going to be. So mathematically, that does mean we're going to introduce a couple of different pieces of terminology to go through and understand our waves. So we're going to be doing that for the next, I don't know, 30 minutes. So let's just get through some terminology to better understand what's going on with our waves. So this here is multiple oscillations for our source, whatever they happen to be. And we want to be able to go through and explain our source. So a lot of different sources, we can talk about what are the period and the frequency in conjunction with information like the root mean square value, the average, and so on. And we'll get to those here in a second. So period, which is going to be represented with a capital T, is defined as the amount of time it takes for one complete sine wave. So for a complete sine wave, we need to go from 0 to +1 to 0 to -1 back to that 0 value. So if we look at it, we're going from 0 to the +1 to 0 to -1 to 0 again. That is one complete sine wave. Same thing is true if we do it with a cosine or some other smooth curve. And so the time that it would take to go from my first 0 to my third 0 is the period, which is going to have the SI units of seconds. And again, it's the time it takes for one complete sine wave. So it has to, basically when it starts to repeat itself, a full sine wave has passed. The other main terminology that we have related to time is going to be the frequency, which is going to be represented with a lowercase f, and it is related to the waves per second, and its SI unit is the hertz. So anytime you hear hertz, that is telling you how many things per second happens. So in this case, if we had 60 hertz, that would tell us that 60 waves pass every 1 second. And we can relate the two of them using this equation here. Period is equal to 1 over frequency, or frequency is related to 1 over period. It doesn't matter what that is. So the good news is that if you look up anything associated with frequency and period, this is it, no matter what type of motion that you have. So this will match circuits, this will match stuff that happens in dynamics, it'll match any sort of thing that oscillates back and forth. This terminology is the same. Any questions about frequency and period? So this is going to give rise to a couple more just terminology values. So again, this is the same sine wave. So first we have the instantaneous value. This is what is the current or the voltage for my source at this exact instant in time. If we are dealing with instantaneous current or instantaneous voltage, and we're just dealing with that specific value, we basically go through and treat our circuit the same way we have before, where we would take our AC source, replace it with that specific voltage or current source value. So instantaneous values, what is the current or the voltage at an explicit time? And we can't really go through and talk about that quite yet. We need our information about the sine wave, which we'll get to at the end of class today. So we'll get there. We're not quite ready yet. We also have what is referred to as the peak to peak, or peak to peak is that's the peak value. This is also sometimes referred to as the amplitude. So that is going to be what is the maximum and minimum values that you're going to have. So this is sometimes referred, right? This is our positive peak. And then down here, we would have our negative. We have two different peaks that we go through and have. They will have equal magnitudes. So the value of the absolute value of the negative peak will be the same as the positive peak, assuming we do not have a second or a DC source in conjunction with our AC source. But we'll talk about that next time. But I do want to just put in the caveat, not technically always true. We also then get the peak to peak value. So that is the value between our two peaks. With peak to peak, we are going to always see this represented as a positive value. So you either add the two magnitudes together, or you go through and you subtract out the -1. Typically with the representation, you would add the magnitude of your positive peak plus the magnitude of your negative peak. So when we move forward to talk about our equations, when we look at something a little bit more generalized, we are going to be seeing A used to represent that peak value. Because A is typically the letter utilized amplitude. And this means that when we look at our generalized equations, that can apply for current or it can apply for voltage. It doesn't matter which one, we can go through and utilize that general formula. So let's look at some of our first equations, because if we think about going through and trying to explain this particular image here, talking about the instantaneous value, that's not too bad in going through and saying, well, hey, that's the maximum and this is the total difference between them. That's okay. Mathematically, it turns out these don't always help us a ton. So this is going to be where we need to introduce a couple pieces of terminology. So the first is going to be the RMS value, where RMS stands for root mean square. So when you hear root, what type of root do you think of when it's a mathematical thing? It is indeed the square root. What does mean mathematically? Yep. So it's a square root of an average. So the square part here being that it is actually a square root, it's not a cubic root or anything along those lines. So with this RMS, this is also going to be referred to as the effective value. So effectively, if I was to take out my AC source and replace it with a DC one, this should be the value that I have to capture the overall general behaviors for my circuit. So the RMS value for a sinusoid voltage, sorry, I could not type there. And again, so the RMS value, which we'll get to the equation here in a second, is equal to so if we have an RMS, sorry, we have an alternating voltage source. If I calculate the RMS value of that voltage source, I could take it out and replace it with a DC source with that particular value. And I would get the same amount of heat in a resistor as the sinusoidal voltages. So this is going to go through and look at heat, which we talked about at the very beginning of class, which we then said, hey, it's not really important until way later. Here's the one place that it's important. So by going through and looking at the RMS value, again, it's going to be the same amount of heat dissipated through our resistor. It is not going to give us the same current values all the time and things like that. So these are the equations that we have for root mean square. So RMS is going to be equal to 1 over the square root of 2 times either, so VP here is our peak voltage and IP is our peak current value, where 1 over the square root of 2 is equal to, with the rounded value, 0.0707. Now, if you are curious where this mathematical proof comes from, if you go through and look at Appendix B, on page, trying to figure out which page it is, on page 972, it goes through and it does the proof to show where this value comes from. It has to do with an integral for, typically it's being done with the positive part of our sine wave. So if you're curious, it does have mathematical relevance, but it's not that interesting of a proof to do in class. Also, I'm pretty sure a majority of you would be upset if I made you do a Calc 2 proof in circuits. So we'll skip it. If you're interested, it's there. Or if you want to talk about it outside of class, I am happy to do so. So we get these two values. And again, this is our, right, VP is peak voltage. And IP is peak current. So let's say, hypothetically, we had the RMS value and we wanted to find the peak value. What would we need to do? We have RMS and want to find the peak. What would I need to do?
About the square root of 2.
Yep. And I kid you not, that is proved in the textbook. So, yeah, if you have RMS, you want to go to peak, just multiply by the square root of 2. That'll get the value. You can, not that it is recommended, you can do the RMS for the peak to peak value. Typically not the thing that you want to do. So more often than not, you just have the peak value. If you need to find, let's say you have RMS and you're asked to find the peak to peak value, use RMS to find the peak, and then you would go through and double it. So if that's something you need to do, go through and do that. Any questions about RMS, or again, root mean square values? Yes.
So that makes peak to peak would be 1.4.
Yep.
Okay.
Yeah, trying to remember what the textbook uses for its rounding. The textbook for all of its things will round it to 1.414. So it'll keep 3 decimal points for all the fun math we're about to learn to do. Any other questions about RMS? So before we go into the next slide, what is the average value of a sine wave? Yeah, so the average value of a sine wave over one complete cycle is always 0. It doesn't matter what the peak is. This is just because all the positives and the negatives cancel out because a sine wave is symmetrical. So this means that if you are being asked for an average voltage or an average current, we are only going to go through and look at half of a cycle. So here we have a voltage-based sinusoid. So if I wanted to find half, I would only go through and look at this positive part here and go through and calculate that average, which turns out to be 2 pi times the peak value, again, with whatever that peak happens to be, voltage, current, either one. So you can use pi over 2, or with the textbook, it is going to round it to 0.637 as the value. Sorry, 2 over pi. I believe that is also proved somewhere. That is also proved in Appendix B. So again, happy to talk about it outside of class, but it's an area under a curve. All right, so any questions before we do our first example? So we are looking for a couple different values here. So why don't you go ahead and try to find what they are. Anybody want more time on 8? All right, how do you find the peak value? Okay, and that happens to be what numerical value? 25 volts. How do I find peak to peak? I double the value. So 2 times 25, last I checked was 50 volts. So for both RMS and average, I'm gonna need to take my peak value and multiply it by the appropriate number. For RMS, what is that value?
707.
Yep, and then what about for average?
Two. 0.637.
Yeah, 0. You can, I'm not gonna stop you guys if you wanna use the actual values. If you wanna use the, 2 divided by pi, by all means go through and use 2 divided by pi. That's fine with me. Or you can use the rounded values, that's okay. So taking those and plugging them in, rounding, we should get 18 volts and 16 volts. Any questions about 8? So we're gonna go back and we are gonna now try to go through and start finding out how can we write out equations to explain this sign. Before we go through and do that, we do have to talk about the fact that we are going to be utilizing our information for sinusoidal AC sources in radians. There will be, and this is, I understand this is gonna be very awkward. We're gonna oscillate back and forth between degrees and radians depending on if we are using the sine function. That's gonna be in radians. And then when we talk about phasors, which we'll introduce on Monday, and then we'll talk about more as we get into our L and RC circuits, we'll do phasors there. For some reason, those are sometimes in, and by sometimes I mean mostly in degrees. So we'll be flipping back and forth as we go through and do that. I am not expecting you to have the unit circle memorized because I don't think I could, outside of like 3 different, I could draw a unit circle. I don't think I can put any values on there outside of 0 and 90 when it comes to putting the degree and radian things on there. So pick a unit circle that you like, go ahead and use that one. If you decide to manually convert between degrees and radians, there are equations for that. So if you have degrees and you want to go to radians, you'll take your degree value, multiply it by pi, divide it by 180 degrees, and that will get you your radians. If you need to go from radians to degrees, it's flipped, so it's 180 degrees times your radians divided by pi. If you do that, you can create your own unit circle. Again, I am not expecting you to create a unit circle. I will give you a unit circle. If there's a unit circle you like, and it's your favorite unit circle, send it to me, and there's the chance that'll be the one that I put on the equation sheet for exam 3. Otherwise, I'm just gonna Google and the first one that looks clear, I'll use that one. So if there's one you like, let me know and we can get that worked out. And again, I'm not expecting you to go through and have this memorized. The reason we need to talk about degrees versus radians is because of this thing called phase. Has anybody heard of phase when it is related to sine and cosine before? All right, cool. All right, so sine starts at 0 degrees or 0 radians, whichever your heart desires. and then we move to the positive peak. And we move to +1, and the question and it looks something like this. So technically with the zeros, they do have names, which was mind blowing to me. Once I started teaching this class, I just thought they were called zeros, but circuits apparently cares. So here we have what is referred to as positive going zero. So after that zero, you'll start having positive values. We hit our positive peak, and then we have our negative going zero. So we'll start then having negative values. And then we get to our negative peak, and then we get back to our positive going zero. So the question becomes, what if we don't start at 0 degrees or 0 radians? I need to be able to go through and have an equation that's accurately going to explain what is going on, because with in technicality with an AC source, whenever you start looking at it, that is going to be where your time is equal to 0. And so because of that, sometimes you're not very good at starting at exactly a sine wave. So you would need to introduce these things called a phase shift or a phase constant. And that is going to be represented with a phi. So in this textbook, it utilizes this variant of phi. So the complete circle with the line through it. If you look at other sources where it talks about phase constants, it will still be phi, but it'll be the other version where it looks a little bit really bad at this one. Kind of like this. So it's like it's not the cursive version, it's one motion. So it still kind of looks like a circle, but one side's a little bit larger than the other. And it still has that line through it. So both phis. I'm going to use the one on the left because that's the one I can actually draw. And that is conveniently what this textbook uses to represent it. So again, it's called a phase shift or a phase constant. Same idea with it. What's cosine of 90 degrees? Okay, what's cosine of 0 degrees? What's cosine of 180 degrees? What? Negative 1?
Oh,
It looks something a little bit like this. So here A is our sine and B is a cosine curve. And would you know it? They're just shifted versions of each other by that 90 degrees that exists between, right, where we have sine and cosine being equal to 90 degrees or equaling 1 for their values. So there are two different ways we can go through and explain the relationship between the sine and the cosine graphs. So again, B here is cosine and A is sine. So because if we're thinking about our unit circle, it starts at 0 degrees or 0 radians. That is where cosine has its maximum value. And as I go to 90 degrees, I am decreasing cosine, increasing sine until I hit 90 degrees where cosine is 0 and sine is going to be equal to 1. And this is why B leads A by 90 degrees. It reaches a maximum 90 degrees or pi over 2 radians before cosine does. So we can say B leads A by 90 degrees, or we can say A lags B by 90 degrees. We'll talk about what that mathematically looks like here on the next slide. So with the phase constant, or I'm gonna call it phase constant because that's how I learned it in physics. Call it phase shift, it doesn't matter. Want to go through and understand if it's leading or lagging, because that's going to determine if it's going to be a plus or minus phi inside of our equation for sine. Any questions before we see the general expression for the sine wave? Oops, did not animate that. All right, so if I have purely a sine wave, so here we are assuming our x-axis is our angle in degrees or radians. Our y-axis is voltage or current. I would have y is equal to a sine phi. For this y here is voltage or current, depending on the type of source we have. If we need to include a phase shift, what we will have is we have two versions. So both of them is, again, it's going to be whatever the instant. So the y value is really the instantaneous voltage or current value. It's equal to the amplitude. So that's our peak current or voltage value. Sine theta, which again is where are we in terms of our source, minus plus phi. Where phi is again our phase shift, and it's negative when the sine wave is lagging or shifted right, and positive when leading, shifted left. So again, with this shifting here, you want to be able to go through and figure out if it's leading, lagging, and that's going to determine what's going on with our sine. More often than not, what we end up seeing for this equation here, which again, doesn't technically matter for current or voltage, we see it represented as y is equal to a sine theta minus plus phi. So in this particular case, the negative sign indicates that the wave is shifted to the right. It is backwards from what we typically associate positive and negative with the left and right directions. So they are flipped, which is why it's minus plus. Minus goes to the right, positive goes to the left. Any questions before we try an example? I want you to go ahead and set up the equation for your sine wave here. Making it such that the only unknown is going to be theta. Does anybody want more time setting up their sine? All right, so let's start. Is this a current or a voltage sine? AC source? How do you know? Great. And what does that 15 volts happen to represent? It's the peak value or the amplitude value. It is A. So V. So if we know what type of source we have, typically we replace Y with the appropriate variable. So V for voltage, I for current. So we'll have 15 volts. We are going to have a sine. It tells us that because of it being the reference here. Theta is going to change as we go through and look at all the different parts. We're just going to keep that as a theta here. And then what else do we have? What's our phi value? It's not 0 in this case. So we have 30. So it's, in this case, it is given to us in degrees. Everything's in degrees, so we can keep it in degrees. Is it leading? So sine wave A leading or lagging B? It lags. And A is referred to as the reference. So A, sine wave A is just sine theta. It is just a sine. So that means that what we're solving for here is sine wave B. So is B leading or lagging? So B is leading. So does that mean phi should be positive or negative? So B is leading. So we are going to want the positive phi value. So because we're looking for the instantaneous values of sine wave B and B leads, it is going to be positive 30 degrees. Any questions so far about 17? All right, so what do we do from here? Yep. I'm gonna plug in each theta value to go through and solve. So for the sake of argument, you know this is going to be 15 volts. Because I have to write this a bunch of different times, I'm going to drop it or indicating it's a voltage in our equation. We're going to have 15 sine 30 plus 30. We're going to have 15 sine 45 plus 30. We're going to have 15 sine 90 plus 30. We're going to have 15 sine 180 plus 30. We're going to have 15 sine 200 plus 30. And we're going to have 15 sine 300 plus 30. What is something we should probably be careful of when we go through to plug all of this fun stuff in? What are the 30s, the 30, 45, 90, 180, 200, and 300 are all in what? Radians or degrees? They're all in degrees. And in this case, phi is given to us in degrees. So when we're plugging this stuff into a calculator, it should be in what mode? Should be in degrees. So this does mean that when we are writing this stuff out, you should put a note somewhere so you know what you're doing, that it should be in degrees or radians. For this particular example, it is in degrees, but not all examples or not all questions will be in degrees. So just be careful with it. Somewhere acknowledge that you know what mode your calculator should be in. That way, if you do mess it up, that you at least have acknowledged it should be in the other mode. So we have 15 sine of 60, which should give us, right, 13 volts. So that is one of our million different answers that we need. And I'm gonna be honest, I don't have the values written down. So let me grab a calculator and we'll just quickly plow through all these unless you two want to just give them to me. All right, cool. 15 sine 75 to 2 sig figs. What? It's 15. Sine of 75 is not 1, so it shouldn't be 15. What?
14.
14. Okay. It's 15 sine 120. The 14 again? Is it? What is it? I don't have them written down. 13. What about 15 sine 210?
You do 7.5.
Okay, what about 15 sine 230? What?
-11.
Okay, and then 15 sine 330. Negative something.
7.5.
Perfect. Fun and thrilling information. You'll do it. I think you have one tedious problem like this on the homework, and then I promise you it gets. So any questions about AC sources so far? So next time we'll go through and we'll introduce the phasor, which is another way to represent our AC source. With phasors, it tends to be more useful once we start getting into circuit components that are not just a source and a resistor. So we'll put a pause on that and then we'll go through, and next week we'll introduce our first new circuit thing that's not a source in the class. So I will see you guys next week.